everyone. Welcome to the session on lessons learned building natural language processing systems in healthcare. I would like to take this opportunity to remind every attendee to ask your questions via the chat throughout this talk. It's located on the right of the screen. Now it's my honor to introduce our speaker tonight, David Talby. I hope I pronounced your last name correctly.
Yep.
Okay, great. David Talby is a Chief Technology Officer at John Snow Labs, helping fast-growing companies apply natural language processing and AI to solve real-world problems in healthcare, life science, and related fields. David has extensive experience in building and operating web-scale data science and business platforms, as well as building world-class agile distributed teams. Previously, he led business operations for Bing Shopping in the US and Europe with Microsoft's Bing Group, and built and run distributed teams that helped scale Amazon's financial systems with Amazon in both Seattle and the UK. David holds a Ph.D. in computer science and master's degree in both computer science and business administration. Now, please welcome David, and I will close my video.
Okay, great. Thank you for the intro. My mom would be very proud. What I'd like to help you with today is really sharing some lessons learned, building systems that actually apply in NLP, kind of the latest and greatest deep learning, transfer learning techniques in real healthcare systems. So we're going to do a short introduction to talk about what the latest research in the field potentially enables us to go and productize and implement, and then talk about the three main things that I think you should know. But of course, the whole goal here is for me to also learn from you. So please share any questions, any chats, and I think I'll kind of ask you questions as you go. I'll have to go to this screen to actually read your questions. So I'll do it every section. We'll do some questions at the end. So IEEE Spectrum has this nice infographic of AI versus doctors. And what they do is they track different papers and see kind of how well are we doing, humans versus the most recent research, which is not really fair comparisons because really the AIs are moving and the humans are not so much. And in 2017, one of the biggest kind of question was can machine learning, deep learning, NLP, can it understand really human nuances, human emotions? I mean, yes, you can understand kind of how things like some images or some music, but can you really understand kind of the nuances of healthcare? And in 2017, we got an answer that basically said yes, because we had 4 separate papers that looked at predicting suicidal behavior, psychosis, ADHD, and autism. All of which require talking to a patient, looking at things like body language, types of speech, style of speech, really very nuanced factors that psychiatrists train on. And we saw that yes, we can definitely do better than humans there at the academic level. 2018, there was a different questions that we tackled, which was okay. Maybe AI can do NEL, but it's super narrow. What happens if we give it kind of broader challenges? And 2018 was really really impressive year in the sense of showing that AI problems focused on text understanding and natural language processing can actually handle really the breadth of clinical diagnosis and care. We had one algorithm that passed China's medical licensing exam, where half of the cases are just patient cases. I just describe you, here's the patient, they're coming in, here's what they have, here's the history, what would you do? Okay, so this is not a memorize and match kind of simple passages. And also in China, China has really been a leader in this space. They had a system that actually diagnosed 600,000 kids over 18 months in a real hospital, and showed that they outperform really everyone other than the very senior physician. So basically, it gives everyone the same level of accuracy that senior physicians give. 2019 was a breakthrough year in reading comprehension. And if you're familiar, I'm not going to go into detail into the SQUAD, the Stanford question answering dataset. but it's a large data set, and they had Squad 2.0 that extended it with unanswerable questions. Basically kind of an SAT-like reading comprehension multiple question test. I'm sorry, not multiple question, it's an open question, right? So you read the paragraph, I ask you a question, you need to answer about the paragraph. And in 2019, we also got to a point where on those benchmarks at least, machines beat humans, beat the human baseline. And the human baseline was, people from where English is the first language, or either high school or college educated, depending on kind of which data set you look at. So that's where we are. And today, we keep going, and research is advancing very quickly. What we've seen is generally, if you have a well-defined tasks, and it doesn't have to be very narrow, but it has to be well-defined, so you can actually have a metric that you optimize. Usually you can match or exceed human performance, human accuracy on it. And of course, there are many academics, startups, companies who are doing that for very specific use cases, and it's going to take us 2 or 3 decades to go and implement all of that. This talk is about 3 lessons learned that at least I and my teams have learned while building systems that do just that in the healthcare space. And the twist is that the 3 things I'm going to talk about are about implementing those algorithms in the real world, in real healthcare. Because all the examples I gave you were academic examples. Okay, an academic research, which means that pretty far off, right? So right now, if someone is depressed, or we suspect autism or schizophrenia, we don't send them to an algorithm. We still send them to a psychiatrist. Same thing, we need to diagnose someone for cardiology problem, oncology problem. We're probably 2, 3, 4 decades away from coming and saying, no, you really should talk to a computer before a human. So now we're really in the very early days of starting to go and productize those systems. There are a few things we've learned. And here are those 3. Before that, I'll just check if there are any questions. Nothing so far. If you have questions, write them. I'll check at the end of every section. So the first thing to know, if someone tells you that they have a system that understands healthcare, understands the language of healthcare, there is no such thing. There are many, many languages that we as humans speak every day, and definitely within healthcare, there are at least several hundred languages that are kind of widely spoken and understood. And here's what I mean. Here's one example. This is kind of a patient record from a hospital visit. It's scanned. You can see, first of all, you can see it's not in English, in the sense that if you're not a medical educated person, if you're not a medical student, you probably can't read this and understand what's wrong with this person. You have everything from your vitals, you have some measurements, you have some lab results, you have a list of medication, and you have kind of the description of what's going on with them and what was the plan and what we are going to do. So out of this text, which is messy, we need to extract things like symptoms, vitals, labs, diagnosis, the actual plan. For example, can we read this and automatically know what medications to order, what labs to order? And the challenges here are, of course, it's its own grammar, its own vocabulary, a lot of jargon, a lot of abbreviations, and just the quality of the document itself, right? If it's scanned, these are not sentences. So that's one example. Here's a completely different example. Let's say you do healthcare and you do chat, or you do messaging, or you try to kind of converse with people. So you have these kinds of SMS or chat style interaction, and this is a very, very different language, right? Because it's first of all, also we don't speak in full sentences. We break sentences. We speak in shorthands. We speak in jargon. I don't have to tell, if I'm speaking to you, I don't have to even say that I'm speaking to you. It's obvious in the context of the conversation, right? So we don't have those things. There's a lot of slang, even profanity, right? And in texting, actually, the more profanity you use, it means that the closer you are to the other person, in high contrast to, for example, customer service calls. And we have emojis, which is its own language to just tell you how I feel about something. So that's obviously basic NLP algorithms like sentence segmentation, tokenization, entity recognition, even sentiment analysis will not work this text before you really understand how this is read. To a completely different example, a lot of the work in health is going to say, okay, can we automatically read, say, PubMed articles, abstracts, and answer interesting questions like, is this study, is it theory or research? Is this, about a stage 1, 2, or 3 trial? In terms of reproducibility, was it a double-blind study, right? Was the sample size? Did they report all of the experiments, yes or no? And to do that, you need to understand how academic papers work, right? So we have the title, which is keyword heavy. We have the abstract, which is really the great, the summary, a very well written summary. We have the introduction and related work, which are actually about background work, though not about this article, right? Then we have the kind of the content of what this paper is about. Then we have things like, discussion and kind of future work, which you need to know that they're actually not about this paper, right? It's about other stuff. And then you have, you have reference and citings and other things. You need to understand that structure in order to be able to extract anything out of this. Also, in this case, we actually use full sentences, correct English grammar, and actually we tend to use long sentences, right? Which also means you need a different set, basically, of language models and algorithms to read that correctly. Other than within healthcare, really each specialty is its own language. So this is an example of a project we did with Roche, the pharmaceutical company, and the goal was to be able to read the pathology report, specifically in the area of cancer, of oncology, and extract very specific things like, where is the tumor? Is it metastatic or not? Meaning, is it spreading? What are the histological values? And specific thing about the specimen that the pathology was about. This is super common in healthcare, right? So if you, mostly if you read a note, you don't always care about extracting signs and symptoms and diagnosing medication. You have specific questions that are about a specific specialty. So if you're in cardiology, you have a very different question. If you're a dentist, you're going to have very different questions. And these are very context specific and have their own vocabulary, their own grammar. Other than that, if you look at this document, of course, you have handwritten notes, you have markings, you have tables, you have key value pairs, right? So there's a lot of assumptions about how the information would actually appear there. So here you need OCR, you need the identification, and then you need to really train a model that understands this specific language. Other than that, of course, there are many, many other formats. Other than specialties, there are formats like just email or FHIR or other healthcare-specific formats, where it's good to remember that those are the strings you get, right? When you say you're dealing with text, so you get those completely different strings. And that's what, first of all, that's what your software has to deal with. Other than that, of course, even with email, the language itself is going to be different. So the way I speak to you now is not the same as I speak to my kids, not the same as I speak to my wife, not the same as I write emails, not the same as I write, an academic paper or patent application. Right? Each one of us, we use many, many different languages each day. Specifically in healthcare, they actually are different languages in the sense that they're different vocabulary, different grammar, different meaning, which leads to different algorithms. Okay, and that's, if we are coming to implement and automate this, it means that yes, these algorithms will actually be different. If you're doing deep learning, yes, the optimal, even just network architecture, definitely the hyperparameters and such will be different. And if you think about it, if you want to be a dermatologist and you want to really understand that language, yeah, you have to go to school and learn it for a while. Understanding cardiology or understanding dermatology takes as much time as it will take you to learn, Portuguese or Russian. That's the reality of it, because the languages really are that different. So that's really the first thing. I mean, if you only take one thing from this talk, just say that there's no such thing in a sense as healthcare NLP. It really is the same. If someone says, I'm talking healthcare, they might as well say I'm speaking human, right? I know all the languages, which is obviously not the case because we have several thousand human languages. And the first thing to ask is, okay, what do I really need to get out of this text? Just checking on questions. No one yet, so we continue. The second thing that's really important about healthcare NLP and healthcare NLP models is that they don't generalize. And I used to write this I used to make this statement with caveats. I said they usually don't generalize, they rarely do not generalize. Sorry, family here. But really, I have to say, I've been doing this for 8 years, and I've yet to see an NLP model that actually generalizes across the data set it was trained on in any meaningful way. And because really the first questions that people usually ask is look, there are, the pre-trained models, right, in model hubs. They're off-the-shelf model. Why can I use it? And there's a really simple answer. Please use it. Please try it. I mean, it's your responsibility to actually give it a go. It's not going to work. And here's one simple example. Here are 6 kind of open source and cloud-based just NLP libraries. All of them except the Amazon ones have a web UI where you can actually copy-paste your text and see what the results are. Which means that you should absolutely do it for your own text, your own project. Maybe it will work. Right? Take you exactly 5 minutes to check all of them. So you should. Don't take my word. But here's what you should expect. Here's an example from a Kaiser Permanente project that we have done, and the goal was to be able to as one of the parts of this part of the project was around trying to predict which patients who have come to the emergency room will likely be admitted. Okay, and the problem is that when someone comes to the emergency room, there's fairly little structured data that you have on them. You have their demographics and age, gender, the previous visits, things like even day or week or weather, other things. But generally, if someone has, say, acute abdominal pain, right, so severe, stomach ache, maybe they have cancer and they're going to stay for a long time. Maybe they have appendicitis and they stay for a couple of days. Maybe they just have gas, right, and they go home 2 hours later. And the only way you'll know is if you read those notes. And if you look at those notes, which seem very cryptic, but when I show this to doctors, say, yeah, this is how people write. This is what we need. We don't need long stories. They do not mention the words patient or pain. None of the sentences are valid English sentences. There's a lot of jargon. So upper ABDs, upper abdomen, took Alka-Seltzer approximately 0.500. It's probably time of day. Nausea, no vomiting. Great. Grammatical structure plus nausea, meaning that the patient is nauseated. 10/10 is the level of pain, but really you need to kind of be in healthcare to understand that. And we want to extract structured features. Okay, where does it hurt? When did it start? How much does it hurt? Did you take something at home so that we don't overdose you? And if you look at these 3, 3 types of, 3 strings, out of the 6 engines that I showed in previous slide, for all of them, the only medical term the 2 of them recognized said that they recognized Tylenol. They said it was a product. Okay, so that's what you get off the shelf, and that's fairly typical. And those are general NLP. If you work even with healthcare, kind of just healthcare NLP, libraries, models, APIs, you get slightly better, but not much better. Definitely not in specialty-specific examples like this. So what you need to do, you need to train your own models. What you need to know, though, is the problem is not just with general NLP library. The problem is you'll have this problem even if you train the model for one specific task. And here's one example of a project we've done a few years ago. And the goal was to automate clinical coding for outpatient radiology, which means radiology means that you go and you do an X-ray or a CT or an MRI or an ultrasound. There's a bunch of them. And the goal here was really just to be able to read the report, which is usually, and the reason people like outpatient radiology is because it's the simplest case. Because it's what is a one-page reports, often templated. And the only goal here, so clinical coding basically is the question of what code should I build for this procedure. And specifically what we focus on here is the procedure code. So basically, if someone came in and they did a CT, for example, what happened? So I need to know, oh, they did a chest CT with contrast. Okay, kind of what was the procedure? So no family history, no personal history, no nuances. And you can see here a comparison. So we had 24 clients. We trained the model on one of them, and then we use it to measure accuracy on the second. Between those 2 clients, there was a 90% overlap between the actual codes, the procedure codes. So meaning those 2 clients largely do the same things. Okay, but here's what happens. You have a model that was trained, gave you 90% accuracy, almost 90% recall. I'm sorry, 90% precision, almost 90% recall. And when you use the same model on the second client, you get 60% precision and 10% recall. Okay, which basically means 10% recall means that 9 out of 10 times, just the model said, I don't know anything, I have no result, to give you. And 60% precision means when the model does give you something, almost half the time it's wrong. Okay, so you understand, as a product manager, we just look at it and say, just turn it off. This is embarrassing, right? Most of the time it doesn't do anything. When it gives you something, it might as well, randomize. And this is what we've seen consistently, even on a super specific, fairly simple specialty task. Because what happened in healthcare is that people just speak differently. And you see it even within the same hospital. You have internal medicine A on the 6th floor, internal medicine B on the 7th floor. And the languages, the templates, the guidelines, the jargon they develop is completely different. Because people work together, a team of doctors and experts, they work together for 10, 15 years. They have their own jargon. This is really just what happens. So, if you're trying to automate this away, you need to understand that this is the reality. And if someone sells you a model and they say, oh, I trained this on this, 5 years worth of data for Mayo Clinic, that's great. It probably will not work on your data. Okay, most likely. And your question needs to be, okay, so how do you train this? Okay, and in reality, here's what you do. If you look here on the right, there's definitely software and assets you can reuse across projects. So for the actual deep learning algorithms, transfer learning algorithms for clinical named entity recognition, entity resolution, negation detection, so telling between, patient is diabetic, patient is not diabetic, patient's mother was diabetic, family history of suspected diabetic. Diabetes, you need to know the assertions. You can do healthcare spell checking. You can do healthcare part of speech models, which are different than general part of speech because really the language is different. You can reuse embeddings, you can reuse transformers, you can reuse terminologies. Okay, but other than those algorithms and kind of pre-trained terminologies, embeddings, transformers, you will need to train models. And really today, the classic design pattern for NLP is pre-train and tune, right? So you have some pre-trained neural networks, transformers, embeddings, whatever, but you do tune it for a specific use case. So whatever library you use, you need to make sure that models are trainable. You need to make sure that pipelines are configurable so that you can do some feature engineering. You can change the lemmatizer, change the tokenizer, change the embeddings you use, even maybe change hyperparameters, and make sure you can very efficiently and very easily train local models. And you also want to support the identification. Not just because for privacy and security and compliance reasons, also because otherwise models tend to overfit to specific doctors or specific patients, right? Which you really don't want to happen. Any questions so far? See? Yes, so yes, definitely always fine tune. Let's see, how do we factor the problem of badly transcribed patient records? So patient doesn't speak English, relies on translator, but something could be lost. Yes, so that's another challenge in healthcare in general. The medical record does not reflect what happened to the patient. So if you think, and one of the mistakes that projects make is they kind of say, oh, because I have access to all of your medical records, then I know what happened to you as a patient. But as a reality, just so that we know, when I get sick, oftentimes I don't do anything, right? I just wait it out for 3-4 days. Right, so that's not anywhere. When I go to the doctor, I don't tell her anything. I don't tell her everything. Tell, listen, I came because I have this ear infection. I need you to give me something for the infection. Let's not do the full history. Okay. Sometimes, yes, there's miscommunication between the doctor and the patient. Right. The doctor sees the patient and comes and says, oh, here's what the doctor thinks is pertinent and important, and this is what the doctor should document. On top of it, you have 5%, which is just fraud and waste and abuse. And you have doctors that are completely overworked, which is why sometimes the doctor is not the actual person who's actually doing the writing. So as a result, there's a huge gap between what actually happened to the patient and what was recorded. And really, this is not something that an algorithm can solve. This is something you need to understand as part of your kind of product or use case, and you need to deal with those limitations. So yes, so diagnosis, labs, medications are not facts. and you should know this. Metrics for evaluation, there's a question there. Usually my metrics really, it's precision, recall, accuracy, and you need to see what works best for your use case. And really, you just need to make sure that you sample the data correctly. How many layers? I'll get back to that in the end. There's a specific detail handle. So just 1 second here. Girls, quiet, please. So, quiet, please. I'm speaking. Sorry. Family. Galit, webinar. Okay. Third thing. This is amazing. Only in the virtual conferences area this happens. So the third and really important thing you need to know is that people often come and say, okay, here I have an NLP problem, or when I find an NLP problem, I need to do this. The problem is that there's no such thing really as an NLP problem, because you never only rely on the text. And this actually goes to somewhat to how you deal with the fact that really you don't have accurate data. You always want to combine what you know from structured data and then really just append more information from the text. And how much that helps will depend on the actual circumstances. For example, this is one well-known article on detecting sepsis. Detecting sepsis within hospital is one of the most common kind of AI use cases that are actually being used in hospitals and save patients. And in this paper, what the research team did, they compared a previous work that only used structured data. So patient is in a bed, and what are their vital signs, what medications are they taking, what's the demographic. And then they augmented that by also extracting features from the free text of the notes, so the progress notes of the patient within the hospital. And they show an increase in AUC from 0.67 to 0.86. And if you're familiar with those metrics in general, so in general, anything below 0.70 is not accurate enough to use. Everything above 0.9, you're probably overfitting. So moving from 0.67 to 0.86 is pretty much moving from useless to almost as good as it gets. And that's really what you want to do, right? So if someone says, okay, so for example, in the previous example when you talked about, patient is in the ER, how likely they are to be admitted? Yes, you primarily look at the text, but of course you also take, you also look at the demographics. You also look at, it's important to know how old they are, what other conditions they have they been here before, what the medications are. And you'd always want this to work together. This is another example in the oncology space, where the goal was to build patient cohorts. So build groups of like patients, which is really important in clinical trials, right? To say, okay, can we actually do A/B testing? Are those people similar? And the goal is to just identify people with non-small cell lung cancer, which is the most common form of lung cancer. What the team found here is that if you only use structured data, you only identify about 2,500 people. If you also use the text, you actually identify more like 8,300 people. So using only structured data, you only identify about almost a third of the patients. That's about it. But also, if you use structured data, there's also 1,090 people that you identify, but you shouldn't have. Right? So if you read the text, you see they actually would have been excluded. And the bottom line is that really, look, if you only use structured data, this is completely useless, right? Which doctors know. But now, those are some of the things you can automate and help with. So as a best practice, when you build a system, what you want to do is you want to make sure that really your NLP pipeline and general kind of machine learning pipeline for structured data is unified, is really one. Because the same way you're going to do feature engineering with, oh, can I use these drugs or these labs or these vital signs? You're going to do feature engineering with, oh, can I use this stemmer or this spell checker, or these, word embeddings, or this NER model, right? And you want to make sure that you can experiment together with the pipeline that includes your NLP features as well as your other ML features, okay? Because really there's no such, like no one just wants parts of speech, right? Or even extracted entities, right? People always want to answer kind of a semantic question. They want a recommender, they want a classifier, they want a predictor, which requires combining those together. So overall, in summary, here are the three things that I think are the first thing people should know when they implement NLP projects in healthcare. So first of all, healthcare has many, many languages. When you have a project, think about really which one you're addressing and build to that. Second is really NLP models do not generalize. Right? Do not expect to train one model on data set and be able to sell it everywhere. Do not be sold on someone who tells you they train something elsewhere and they can give an out-of-the-box example. It just does not work. And the third thing is really don't go looking for just pure NLP problems, because that's really not the way it works. What you're looking for are problems where if you have access to the text, whether it's academic text, clinical text, reports, genomic data, whatever, you know that there's important information there that will help you improve existing models. And when you start a project, nowadays, yes, you can match or beat human accuracy in the majority of cases, and in real production cases, and now we do it fairly consistently as well as others. The only thing you should know when you explain to business stakeholders, humans often are not that great. Right, so the very famous case where in China they did very large case diagnosis, AI case, and the kind of the computer reached 65% accuracy, and which some people thought that isn't it very low, until they realized that the average human doctor in that specific set of circumstances only get to 45% accuracy. Okay, so the more complex the task, really the worse humans do it on a regular basis. So when you set the expectation that you're going to match or exceed human accuracy, people should understand what that means. So that's my talk. Of course, if you don't think this is right, if you think there are other things that are as important or more important, please let me know. And I think we have, how are we doing with time? I think we're almost at time, but I'll try to answer a couple of questions. And if not, here are my contact details. So LinkedIn, Twitter, and email, please feel out to reach out. I'm always interested to know what people are working on. And really, just like you, I'm happy to learn and see how we can improve. If I did not answer your question, it's important also, please, email it or send me a message, and I'll make sure I answer. Okay. Shinyon, how will be the time? Should I take a couple of questions, or is it time to close?
It's entirely up to you. It seems that you have addressed quite a few questions during the talk, but we still have questions coming up. So depending on your availability, we can address a few more questions. Our time is up by 7:20, but if you're willing to stay, I believe the audience would appreciate very much.
Sure. Okay, so let me, I can stay for like 3-4 more minutes and answer some questions.
Okay, so let's take some of the questions from the audience. In your experience, what areas of healthcare are most amenable to NLP analysis?
Sure. So the answer is quite a lot of them, because healthcare is about a lot of text. So when you think about what would be a good NLP project, think about a problem where a human tries to solve the problem and first look at the text. Okay. So for example, if you go to a doctor, let's say Dr. A referred you to Dr. B, and you go to Dr. B, right? And Dr. B wants to know what's wrong with you. They're not going to start by looking at your demographics, your past lab results, or or the past past vitals, right? They want to say, okay, show me the note. What did the last doctor write, right? When you last met them, you start with the text. When you're sitting in a hospital, right, and the nurse wants to see what are your post-op instructions, he or she, they just want to read 1 or 2 paragraphs of text, right? So think about cases where a human would know, look, the information is in the text, right? And of course, look, you can guess, what's my likelihood to whatever, to catch a disease because of just my age and my zip code, right? And probably do better than random, right? But the real information would be in my actual clinical record. Right, so really what it means is that EMR records, most of the real information is in text. Okay, and today, for example, if you want to ask like super simple questions, out of the people in the hospital, who is suspected with the flu or suspected with COVID? Right now, what happens is that you sit down nurses and they read one by one and they copy paste it in Excel. Okay, here's one simple example you can do better. But really, any predictive problem around, what's likely to happen to a patient, looking for fraud, looking for kind of identity theft, recommending which, really what's kind of the next best action with the patient, being able to read, especially new kinds of reports. So some data, especially like billing data, medication data is in EMRs. There's a lot of new data that's out of EMRs. So all of the kind of lab reports, genomic reports, all of those really, doctors, they get them as PDFs, right? If you can automatically read that and give recommendations, so that I don't have to read a 10-page document, which I don't have time for, just give me the summary, give me the highlight, you can help a lot of people that way. So I'd say, but really, healthcare is huge. One thing to understand, like healthcare, healthcare is like in the US, it's bigger than retail. Okay, and if you look at the, if you want to say disrupt the entire online education, right, completely replace it. Online education is smaller than dentistry, right? Which is really kind of one of 120 specialties. Healthcare is an immense field. So really, there's a lot you can do there and really help people.
Okay, great. Do you have time for another question, maybe?
Yeah, let's take one more. Yes, and then
okay, one more question.
I'll type my email here. So if I did not answer your question, please just email it to me. I'll be happy to follow up.
Okay, great. So last question. Healthcare has very many specific terminologies, including some that are constantly being updated. Do you retrain the model, fully retrain the model as technologies are updated, or does transfer learning work?
So yeah, so transfer learning definitely works. Yes, and because look, one of the things you want to do is you can, as I just told you here, right? You need to train your own models, right? So if you're doing something, you can say, oh, I only care about stage 4 colon cancer, right? And a very specific question, and tell you would absolutely have its own language. You need to train it. But what you don't want to do, you don't want to start from scratch in the sense, oh look, you need to teach it what blood pressure is. Right, so definitely there's a lot you will benefit from reusing embeddings, using transformers, using neural network architecture, using terminologies. Okay, and one of the one of the biggest, the bottom line improvement in transfer learning over the past really 18 months is the fact that what used to take you, where you needed, let's say even 2 years ago, you needed 10 or 20,000 patients to train. Now you can get to the same level of accuracy with 500 to 1,000 patients. Right? At least that's what we're saying with our algorithms. And it's all transfer learning. Okay, so there's definitely, those are kind of real technological improvements. Absolutely. But other than that, look, terminologies, yes, we have a, and not just really, it's not just us, every major player who's doing this in healthcare. We have a team of clinicians. We update the terminologies, we manually augment them, and then we use them to retrain our models and embeddings regularly. Okay, and that is something you will need to do. Or get, and really, as far as I know, really every major player in the industry does this regularly.
Okay, with that, we have concluded our talk tonight. Thank you again, Dr. David Talby, for a very educational talk, and thank you also for everyone for attending this talk. I wish everyone a pleasant evening or day, depending on what time zone you are.
Thank you very much. It's been a pleasure.
Thank you.